Now we come towards the work. As I have explained earlier, we can explain this value as the dot products of force and displacement. So if we apply force on certain body, the body moves in the direction of force having some displacement. This product of force and displacement gives the value of work. But if the force is resolved into two components like F cos theta and F sin theta, then work can be given in terms of angle. So, work done can be written as the dot product of force and displacement, or otherwise it can be written as F cos theta into displacement, or it is F sin theta into displacement. So, these facts are to be explained in this context. Whenever a force acting on a body displaces it, work is said to be done by the force. Work done by force is equal to the scalar product of force applied and the displacement of the body. Either say scalar product or say the dot product. Now, force, that can be variable force or it can be constant force. So, force means force is an agent which changes or tends to change the state of rest or the state of motion of the body. So, variable force means that displacement is basically variable, and when we speak force constant, it means that work done is constant by the constant force. Work done by constant force, if the direction and magnitude of force applied on a body is constant, the force is said to be constant. Work done by constant force, that is, force into the component of displacement along the force, as I have explained earlier, either the component is F cos theta or F sin theta, or W can be written as displacement multiplied component of force along displacement. Now it is shown in the figure, that is horizontal component F cos theta, and F is resolved into the component F cos theta. Displacement is indicated by R. So originally the block is kept at the left side, and after the application of force, the block has moved and the displacement is R. So F is the force which is resolved, and one of the component is F cos theta. If force F is acting on a body at an angle theta to the horizontal and displacement is R, is along the horizontal, then the work done is given by F cos theta multiplied by R, or it is equal to F R cos theta. This I have already explained in the previous context. Now in the vector form, the dot product of F and R will be work done. So we can write this expression as F is equal to I into Fx plus J into Fy plus K into Fz, where I, J and K are the unit vectors along x-axis, the y-axis and z-axis. Fx means force along x-axis, or the component of force Fy along y-axis, and Fz means component of force along z-axis. R is the displacement, that is I into x plus j into y plus k into z, where I, j and k are the unit vectors along x-axis, the y-axis and z-axis. The work done will be Fx into x, Fy into z and Fz into z. So x, y and z are representing the displacements along x-axis, the y-axis and z-axis, and we will find Fx, Fy and Fz forces along x-axis, the y-axis and z-axis. The same is clear from this figure. Now we come to one of the very important note, the force of gravity, that is weight. Weight is normally calculated by mass into acceleration due to gravity. Is an example of the constant force, hence work done by weight is an example of work done by a constant force, because acceleration due to gravity, that is g, does not change. Now the nature of work, it can be negative or positive. However, the work is a scalar quantity. So work done is a scalar quantity, yet its value may be positive, then negative or even zero. Now we can have the positive work. Now we take the dot product of F and R, which is equal to W, or it can be written in the scalar form, that is F into R cos theta. Theta is acute, means less than 90 degrees. Then cos theta is positive. Hence work done is positive. Now when a body falls freely under the action of gravity, theta will be 0 and cos 0 will be 1. Therefore, work done by gravity on a body falling freely is positive. So these are some examples of the positive work. And then we come to the negative work, where theta is assumed to be obtuse, that is more than 90 degrees up to 180 degrees. So cos theta is negative, hence work done is negative. Now example is, when a body is thrown up, its motion is opposed by gravity. The angle theta between the gravitational force F and displacement R is 180 degrees. Then we take the cosine of this angle, and that is found to be -1. So if we multiply displacement with -1, it will be the negative work. Therefore, work done by gravity is negative. Now we come towards the second point. When a body is moved over the rough horizontal surface, then force of friction is opposing this motion. So the motion is opposed by the force of friction. So once more I will read the context. A body is moved over a rough horizontal surface. The motion is opposed by the force of friction. Hence work done by frictional force is negative. Now the important note is that work done by applied force is not negative. Work done is not negative, however the force is negative. Now we come to the third point. When a positive change is moved closer, when a positive charge is moved closer to another positive charge, that is, the Coulomb law states that like charges repel. So work done by electrostatic force of repulsion between the charges will be negative. Now we come towards the zero work. Zero work means that person moving horizontally. When force F or displacement R or both are 0, the work done W will be 0. Again, when angle theta between F and R is 90, the work done will be 0. Now, first part is, when we fail to move a heavy stone, however hard that stone may be, we may try. Work done by us is 0 because displacement is 0. When coolie carrying some load on his head moves horizontal platform, theta will be 90. And when we write cos 90, it will become 0. Therefore, work done by coolie is 0 in the horizontal direction. That is because theta is 90 and cos 90 will be 0. Now we come about the tension in a string. We consider a simple pendulum, that is a bob and a string. String is tied to a rigid bar, and we find that simple pendulum is suspended from that rigid bar. The weight of the bob will act vertically down and the tension will be against the weight. If we take the difference of the two, that will become 0. Is always perpendicular to the displacement of bob. Therefore, work done by tension is always 0. Now our question is that the work done in pulling a body of mass 5 kg, mass is given on an inclined plane where the angle of plane is 60 degrees, the coefficient of friction is 0.2, that is mu is given 0.2 through 2 meters. So in order to solve this question, the minimum force with which a body is to be pulled up along the inclined plane, this I have explained in pulleys and the inclined planes. The formula is given as mg into sine theta plus mu cos theta. Work done is F into d or Fd cos theta. F is replaced by mg, and then we have written sine theta plus mu cos theta into d, that is the force of friction, and theta is 60 degrees. Sine 60 will be root 3 by 2, and mu is 0.2 and cos 60 is 1 by 2. Root 3 can be taken as 1.732, and if root 2 will exists, it will be 1.41. So if we multiply all these numbers, our conclusion will be 98.08 joules.